Carbon-free ferrocene. Analog, synthesis, structure, and bonding in an all-boron osmium sandwich complex. The synthesis of carbon-free analogues of classical organometallic compounds represents a long-standing challenge in inorganic and main group chemistry. A research collaboration between the Indian Institute of Technology Madras and the Indian Institute of Science has now reported the first true carbon-free analogue of ferrocene. This work describes a neutral osmium sandwich complex featuring two boron-based pentagonal rings, B5H10, coordinated to a central osmium atom. The study provides key insights into metal-ligand bonding beyond carbon frameworks and establishes new directions in boron cluster chemistry and organometallic design. Since its discovery in 1951, ferrocene has played a foundational role in the development of organometallic chemistry. Its structure, an iron center sandwiched between two aromatic cyclopentadienyl CP rings, redefined bonding concepts and introduced the notion of pi coordination between metals and conjugated ligands. The elucidation of ferrocene's structure marked a paradigm shift, leading to the development of numerous sandwich complexes with wide-ranging applications in catalysis, materials, science, and electrochemistry. A long-standing goal in inorganic chemistry has been to replicate this sandwich architecture using non-carbon ligands. Achieving a fully carbon-free analog poses significant challenges due to the unique electronic and aromatic stabilization provided by carbon-based pi systems. Previous attempts toward carbon-free analogues. Efforts to replace carbon-based ligands in ferrocene-like systems have yielded only partial success. Notably, in 2002, a titanium complex coordinated by two 5-membered phosphorus rings was reported. However, this system deviated from true ferrocene analogues due to its anionic nature and differences in bonding characteristics. Similarly, attempts to construct transition metal-boron sandwich complexes have historically resulted in incomplete coordination. For example, in ruthenium-boron systems, only partial complexation was observed, with one boron ligand exhibiting pentahapto coordination while the other exhibiting trihapto coordination. These limitations underscore the difficulty in achieving symmetric, neutral, and fully coordinated carbon-free sandwich complexes. Synthesis of the osmium-boron sandwich complex. The reported breakthrough involves the reaction of a square-planar osmium precursor with borane dimethyl sulfide, leading to the formation of a neutral sandwich complex. The resulting compound consists of a central osmium atom coordinated between two pentagonal boron rings, B5H10, representing the first structurally authenticated carbon-free analog of ferrocene. Each boron atom within the rings participates in a highly interconnected bonding network, forming BB bonds with adjacent boron atoms while also bearing one terminal hydride and two bridging hydrogens, BHB. This unique bonding arrangement contributes significantly to the stability and electronic structure of the complex. Structural characterization. Single crystal X-ray diffraction analysis revealed several key structural features. The two boron rings adopt a staggered, rotationally offset conformation, in contrast to the eclipsed geometry typically observed in ferrocene. The inter-ring distance is notably short, 3.071 angstroms, indicating strong metal-ligand interactions. The reduced ring-ring separation is attributed to the presence of bridging hydrogens and the interaction of boron-based orbitals with the diffuse d orbitals of osmium. Additionally, an isomeric osmium complex was isolated in which the two boron rings are oriented perpendicularly. This coordination mode, along with a tri-hapto bonding configuration observed in another isomer, represents coordination patterns not seen in classical ferrocene chemistry. Electronic structure and bonding. The bonding in the osmium-boron sandwich complex differs fundamentally from that in ferrocene. While ferrocene relies on delocalized pi electron donation from aromatic CP rings, the boron analog exhibits enhanced metal-ligand bonding due to rehybridization of pi molecular orbitals induced by bridging hydrides, B-H-B, contributions from bent terminal B-H, B-HT, bonds, strong overlap between boron-based orbitals and osmium's diffuse d orbitals. These effects collectively result in stronger metal ring interactions compared to ferrocene, as well as unique electronic properties. Implications and applications. The successful synthesis of a carbon-free ferrocene analog represents a significant milestone in inorganic chemistry. Beyond its fundamental importance, this work has broader implications. It advances understanding of metal-ligand bonding in non-carbon systems. It provides insights relevant to boron-based materials, such as borophones, and their interactions with transition metals. It opens new avenues for designing functional materials with potential applications in catalysis, electronics, and nanotechnology, including intercalation chemistry in graphene-like systems. In conclusion, the realization of a true carbon-free analog of ferrocene using boron-based ligands marks a transformative development in organometallic and main group chemistry. The osmium-boron sandwich complex not only replicates the structural motif of ferrocene, but also introduces fundamentally new bonding paradigms driven by boron chemistry. This work bridges the gap between classical organometallic frameworks and emerging main group architectures, offering a platform for future exploration of carbon-free functional materials.